Today, we're going to continue those ideas that we were talking about yesterday. So we're going to continue working with power series and ask for which values of X does the power series converge. And we're going to give a name to this idea. This will be finding the interval of convergence. And this box up here gives a summary of what we can find when we do the interval of convergence. I want us just to jump into this example first, and then we'll go back and look at these definitions. So this problem's asking for the radius and interval of convergence. Really, all that's asking is find the X values that make this series convergent. So just like what we were doing yesterday. So we can start with these problems whenever we're asked to find interval or radius of convergence or find which X values make this convergent. What we're going to start out by doing is either a root test or a ratio test. In this case, either work. I'm actually maybe just going to do a ratio or a root test on this one. Normally I would jump into ratio test, but I want to show you how the root test works here because sometimes the root test works a little nicer. The ratio test is always going to be what you want to use if you have factorials though, but we don't have any factorials. Okay, so I'm going to try root test. Okay, so we're going to look at the nth root of the absolute value. Don't forget in that root test, there's that absolute value. The ratio test also has absolute value. Okay, so I can move that root inside the absolute value. The nth root of 2 to the n will give me 2. The nth root of this piece will give me 4x minus 8. The nth root of n will give me 1 to the 1 over n. Okay, now we're taking the limit as n approaches infinity. The n's are only in the denominator. If you remember from a few weeks ago when we did the root test, we had a theorem that told us the limit as n approaches infinity of n to the 1 over n is just 1. You can prove that with kind of a fancy L'Hopital's rule. So our denominator is going to be 1. We're going to be left with the absolute value of 2 times 4 minus 8. And remember, we're looking for what that's a 4x in there, sorry. We're looking for which X values make this converge. The root test the series with the root test converges if this is less than 1. Same thing with the ratio test. Okay, so what we are going to do here is we're going to solve for X. So we can distribute, we can make that 8x minus 16 is less than 1. Let's rewrite this as -1 is less than 8x minus 16 is less than 1. Add 16 to all sides, so we get 15 is less than 8x is less than 17. And we divide by 8, so we get 15 over 8 is less than x is less than 17 over 8. Phew. Okay, that's a lot of algebra. At this point, the radius of convergence is just how wide is this interval and then half of that. So you could kind of think of like half of this is the radius of convergence. So to get from 15/8 to 2/8 or to 17/8, I add that whole width is 2/8. So half of that is just 1/8. 1/8 is the radius of convergence. The radius of convergence is just telling us how wide that interval is, except for it's just half of how wide it is. Okay, so this is our radius of convergence is 1/8. Okay, the interval of convergence is this, but we still have to check the endpoints. The radius doesn't care about the endpoints because that's not going to add extra stuff, or it's not going to make it wider, except for by a single point. Okay, so we have to check our endpoints like we did last time. Endpoints are going to be a little bit messy here because they're funny fractions, but I'll check them up here. The examples that we're going to do in class are going to be a little bit less messy than this one. Hopefully, the homework examples definitely are. Okay, so I'm going to plug in x is equal to 15/8. So when I do that, I'm going to have 2 to the n over n. When I plug 15/8 into here, I get -1/2. You should double check that, all to raise to the nth power. So now we need to simplify this so we can figure out what this expression does. So it looks like I'm going to have a -1 to the n from here. I'm going to have a 2n still in the numerator. This is going to give me a 2 to the n and an n. The 2 to the n's cancel out. So we're left with -1 to the n over n. An easy alternating series test will tell us that this converges. And so we need to include the 15/8 in our interval of convergence. And now we need to plug in 17/8. When I plug 17/8 into that 4x minus 8, I'm going to get 1/2 out. So my sum is going to be 2 to the n over n times 1/2 to the n. 1/2 to the n will give me 1 over 2 to the n. So the 2 to the n's are going to be or cancel out. We're going to be left with the harmonic series, which diverges. So we will not include the 17/8 in our interval of convergence. So our interval of convergence, which I usually denote IOC, is this expression up here. If we write that like this, we get 15/8 to 17/8, not including the 17/8. Okay, so let's go back up to our definitions up here. So the interval of convergence is the interval of all x values, including any endpoints for which the power series is convergent. That's the interval of convergence. The radius of convergence is just half of that width, okay? This theorem up here tells us that there's 3 possibilities for when we find the interval and radius of convergence. So one possibility is what we just found here. This is the third case. This is where there is some kind of radius involved. In this case, the radius is 1/8. It's also the case that the series converges only at a single point, and that's this first case. And that sometimes happens. That's usually going to be the case if when you do the ratio or the root test, that when you try and set this less than, well, actually that the limit turns out to be infinity at this step. And so that this is never less than 1. There's always going to be a single point that you could plug in that would make it less than 1. That would be whatever point makes this 0. We'll see examples in class about this, so don't stress too much about whether that makes sense or not. And then there's also the case that the series could converge for all x. That's if when you do this limit out that you get a concrete number that is less than 1 and you don't have any x's left in your expression, okay? Once again, we'll see examples of all 3 of these scenarios in class, but it's good to know that our interval of convergence can either be a whole interval, it can be a single point, it can be all real numbers. But if we have an interval, we have to worry about endpoints, just like we did last time.